Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, thank you for this opportunity to present our research titled Portable and Low-Cost Paper-Based Sensor Integrated with Smartphone for Chromium Ion Detection. I am Teguh Pambudi, representing the research team from Universitas Singapura Bangsa Karawang. Today I will walk you through the first is the introduction of this research. Second is research method we employed. Third is the key finding of this research, and the last is the significance of this research addressing the environmental challenge. Heavy metal pollution, particularly from industrial and human activities, poses a severe threat for the ecosystem and public health. Chromium, a commonly used heavy metal, is especially concerning. Exposure to the chromium is linked to the bronchitis, digestive system cancer, and other serious health issues. While numerous methods are available to determine chromium in water, include AAS, ICP-AAS, ICP-OAS, and ICP-MS. But this method come with several drawbacks. First, they are expensive. Second, they are require skill analysis and a complex procedure. Most importantly, they are not portable for field application. Considering the dramatic increase in heavy metal pollution, there is a critical need for the development of simple, low-cost, rapid, portable, and on-site method for detecting heavy metal. This gap forms a foundation of our research. We are developed a paper-based chemosensor using diphenyl carbazide as a chromophore and a silica as a support material for immobilization. And also we integrating the colorimetric analysis using digital image colorimetric. The fabrication of paper-based chemosensor involves two key steps. The first is modification of test paper with the silica. Silica nanosphere will synthesize using a solution of tetraethyl orthosilicate, cetyl trimethyl ammonium bromide, and 3-ethylamine. Filter paper was immersed in the solution, dried, and washed with the hot hydrochloric acid to enhance the surface properties for immobilization and also to remove the excess of the solution. The second method is the immobilization of diphenyl carbazide on silica moderated paper. First, the diphenyl carbazide was dissolved in hot ethanol and coated onto the silica modified paper, and then the DBC coated paper was then dried to create a final paper strip chemosensor. To ensure paper-based chemosensor characteristic, we conducted the following characterization. The first is FTIR characterization. This analysis will confirm the successful coating of DBC onto the paper by identifying the characteristic absorption peaks. The second is SEM analysis. This will be reveal the surface morphology, showing the presence of the silica and DBC layers on the paper. For the optimization, we evaluated three key parameters. The first is pH, to determine the impact of the acidity or the alkalinity on the sensor performance. The second is reaction time, to identify the optimal time for maximum color intensity. The last is the DBC concentration, to assess how varying the chromophore amount influence sensitivity and accuracy. This is the result of our research. The first is SEM characterization. As you see on the screen, that the SEM image reveal the silica nanosphere is uniformly coated on the paper, providing a robust platform for DVC immobilization. This result confirmed that the sensor structural integrity and readiness for the optimization studies. The second is result from FTR characterization. After modification with DBC, several new absorption peaks appear on the spectrum. In the FTR spectrum of the filter paper modified by silica and DBC, an absorption band was observed at wave number 1602, corresponding to the C bonding C aromatic ring stretch vibration. This confirmed by the absorption of peak at 1666 indicated aromatic combination bonds, and also appears a peak at 1538 corresponding to secondary amine. This confirmed that the DBC successfully coated to the surface of the filter paper, corresponding to the diphenyl carbazide structure. Okay, let us now discuss about the optimization result in more detail. The first is pH optimization. As you see on the screen, there is a changing color from the uninteracted paper with chromium. With the interacted paper with chromium, there is a changing color from the white to the purple. Overall, the sensor performance was stable across the different pH level with minimal variation in the color intensity. However, under acidic condition, the DPC coating was observed to dissolve, reducing the sensor effectiveness. The second is the reaction time optimization. As you see, increasing reaction time significantly enhance color intensity up to 120 seconds, indicating that the reaction between the chromium ions and DPC has reached its optimum. Beyond 1020, 120, the color intensity remain consistent, suggesting the no further reaction occur. The third is DPC concentration optimization. As you see on the screen, higher DPC concentration generally resulted greater color intensity due to the increases availability of the chromophore group for interaction with the chromium ions. Minor fluctuation were attributed to the uneven coating DPC on the paper surface was observed. So this is the conclusion of our research. This study is successfully developed and optimized a portable, low-cost, and on-site paper-based chemosensor for chromium ion detection. There are some key findings. The first is the sensor fabrication process was validated through the FTIR and SEM analysis, confirming the successful immobilization of TBC. The second is optimal detection condition include neutral to slightly basic pH, a reaction time of 120 seconds, and higher DPC concentration. And the last, the sensor demonstrated significant potential for rapid and on-site heavy metal detection, particularly for chromium ions. So the future development will aim to enhance the sensor acceptability and compare with the real waste of the chromium, and also broaden its application to detect the other heavy metal. Thank you for your attention. I'm happy to address any question you may have.